In this video, we're going to be talking about molecular shapes using something called VSEPR theory. You are going to need something to write with and something to write on. So once you have those ready, let's go. Okay, so as we said before, Lewis structures are two-dimensional representations. They're drawn on paper. They don't do a really good job at showing molecular shape. What we do is we can determine the three-dimensional shape of a molecule by figuring out how the electrons are actually distributed around the center atom. This is what VSEPR, or valence shell electron pair repulsion theory, does, right? It is exactly what it sounds like. Electron pairs want to push each other away as far as possible, right? So if I have multiple electron pairs around an atom, they are going to want to be as far apart in three-dimensional space as they can be because they're going to push each other. That's all this is doing, is we're taking that concept and applying it to three-dimensional space. Now, please keep in mind when we do this that it may be a little bit counterintuitive how things work out because your brains aren't really used to working in three-dimensional space mathematically yet. You've been covering two-dimensional space, and most of the geometry that you've been doing this year has been two-dimensional geometry. So what we're going to do is we're going to break it down and make it kind of easy to work with. The first thing we're going to do is we're going to define what is called an electron domain. A domain is just a region around the atom that has electrons. It doesn't matter whether it's a single bond or a double bond or a lone pair, it's still a domain, right? So that scene from Lord of the Rings where Legolas shoots down the entire elephant and Gimli goes, still only counts as one. Same thing for domains. If I have a single bond, a double bond, or a triple bond, no matter how many electrons are in that region, that's still only one domain because it's one region. Now, we can classify a domain based on the type of electrons we have there. If those electrons are involved in a bond, whether it's a single, double, or triple bond, that is a bonding domain. If that domain is there because it's a lone pair, that's what's called a non-bonding domain. And when you add up the total of the bonding and non-bonding domains, you get what's called the steric number, which is abbreviated SN. Okay, so steric number is the total number of domains around our center atom because the center atom is the atom that determines shape. So if I had, for example, two bonding domains and one non-bonding domain, that has a steric number of 3. Now, the next slide is going to give you a chart. If you are in the CP1 class, you're only going to have to know about half of this chart. I'll actually draw out the region I want you to know. Once you've drawn those down, you are done with the video. If you are in the honors class, I'm going to go on after you've written down the entire chart. Okay, so this chart right here, if you are in the CP1 class, then you will have to know steric numbers 2, 3, and 4. So this little 3 by 3 box, and by the way, if a box is blank, that means that that doesn't actually form, so you don't have to worry about it. Okay, so CP1, you only have to know 6 shapes and you're good, right? So 2, 3, and 4 steric number, lone pairs, 0 lone pairs, 1 lone pair, 2 lone pair. Honors group, you have to know the entire table. Now, one thing I will start by pointing out is that each steric number has a base geometry. The base geometry is what happens if it's all atoms, no lone pairs. Okay, so if you have a steric number of 2, two things, the farthest apart two things can be is a line, right? 180-degree arc, straight line across. If you have a number of 3, the farthest apart 3 things can be, it's still flat, is 120 degrees. This is what we call trigonal planar. Trigonal because triangular shaped, 120 degrees. Planar because it's flat. If you have a steric number of 4, Now we get into the three-dimensional shapes because it gets a little weird. It's not 90 degrees top, bottom, left, right. It actually forms an equilateral pyramid, right? What's called a tetrahedron. So tetrahedron is a pyramid where all four sides are equilateral triangles. The angle in a tetrahedron is 109.5 degrees. Okay, so once you have your respective set drawn down, CP1, you can stop the video, you're done. Honors, once you have yours drawn down, then pick up the video again, and we'll go on to the next slide, which will be the last one for you. Okay, so the last thing I kind of want to go over with you guys is how lone pairs on the center atom affect bond angle and also hybridization, right? So first thing to keep in mind is that the different hybridizations always have the same geometry. sp3 is 109, sp2 is 120, sp is 180. Now, when you put lone pairs on the center atom, since those lone pairs are typically closer to the center atom than electrons are in a bond, they take up more physical space around the atom angle-wise. Right? So that means the more lone pairs you have on the center atom, the smaller and smaller the bond angle will get. And it only goes down a little bit, right? So if we take sp3 as an example, sp3, no lone pairs, base geometry, 109.5 degrees. If you make it one lone pair instead, so trigonal pyramidal, the bond angle is actually closer to 107. If you go to two lone pairs, so what's called bent 109, that angle is actually closer to 105. Now, you don't have to know the exact differences in bond angles for all of these, right? So you don't have to know that it's 107 or you don't have to know that it's 105. But what you do have to know is if I ask you, for example, what is the bond angle of this molecule that is trigonal pyramidal, right? So sp3 with one lone pair, and I gave you options, you would choose one that's really close to 109 and a little bit under it. So that's what I'd like you to know for that. So lone pairs affect bond angle by squishing them in a little bit. And that's it for the video for you guys as well. I will see you in the next video where we talk about molecular polarity.